Okay, hello everybody. Welcome to my solar lab, the solar lab I'm trying to set up. And one thing I want for this solar lab is I want to be able to simulate a solar panel. And what makes this, maybe interesting is that a solar panel has a, interesting IV curve that that is very important. And the reason it's important is that the way this works is, you have this is called the open circuit voltage. So this is just the voltage across the terminals on the solar panel when you're not drawing any current. And as you draw more current, as you might expect, the voltage starts to sag. And as you draw a lot of current, you sort of hit this cliff and it falls off. And, this is the short circuit current of the panel. Those are two values that you'll see in a data sheet for a solar panel. And you'll probably also see this IV curve. And what's interesting about this is, the power is I times V. So it's sort of this furthest point over here where I and V are maximized, and you get your sort of maximum power point. And, since it's sort of the area of this rectangle, that is the amount of power you're getting. So if you put power on this axis over here, then your power curve kind of looks like this. And the idea is that, if you want to harvest the maximum amount of power, your solar controller needs to operate at the maximum power point. And it can do that by basically changing its current draw until it hits this point right here. So like, there's not, as far as I know, there's not like a lot of other things that have a curve like this. I can't just like use a resistor and a power supply, right? Because the IV curve, of course, is just like a straight line. So I really want this thing that has this sort of like curving bent knee here. And so how do I do that? Well, one thing I could do is I could just use a solar panel. So I have a 300 watt LED here in the lab, and I could just shine it at, one of these small solar panels and connect it to my charge controller. And there you go. I don't have to simulate any IV curve. I'm using the real thing here, and that definitely has its uses. Unfortunately, it's kind of hard to do repeatable experiments because, like, the temperature of the panel matters and all of this stuff. So it's not just the light source that needs to be consistent and repeatable. The actual panel itself, the temperature matters. So I don't really want to have to mess with that just for like basic experiments here at the bench. Okay, so what did I do instead? So over here, I have some block diagrams and schematics drawn out here. So this is what I want to build. So right here is the charge controller that I would be testing, and here's the positive and negative solar terminals, and I want to hook it up to this circuit over here. What I have here is a current source, and it's not just any current source; it's a variable one, so I can control it with this control signal coming from an MCU, and then the MCU also monitors the voltage, over here using an ADC, the voltage across the charge controller. And the idea is that, like, whatever the current voltage is, the MCU can update the current source to keep the charge controller on the IV curve that I'm simulating here. And what this looks like in terms of the actual circuit is, let's just start with this right here. This is a current source. So right over here we have an op amp, and we have a MOSFET. And the way this is connected is, the op amp has this negative feedback from the voltage across this current shunt. This is just a low value resistor, so it's 0.1 ohms. It has kind of a high power value, 5 watts. But anyway, it's getting the voltage feedback here into its inverting terminal. And when you have it set up like this, it means that the output at this op amp, the op amp will try to make the output and the positive terminal equal in voltage, right? So you basically have like an adjustable voltage here. This MOSFET here is just so I can basically drive more current through it than I could with just an op amp alone. So this feeds into the gate of the MOSFET. The MOSFET's set up in this like source follower orientation. So, the voltage it gets at the gate, it will try to match at the source. And so every voltage source is also a current source. If I can set the voltage across this resistor, then that means I'm also setting the current across the resistor. So, so the current being driven through here is, a known value based off the voltage. And then, this MOSFET, the current flowing into the drain is about the current flowing out the source. And so what happens is I have the charge controller up above this entire thing. It's really a current sink. They still call them current sources, but it's really a current sink. And I have the negative terminal of the charge controller hooked up to the top of this thing. And then the charge controller positive terminal is just hooked up to the positive rail. But you know, this current is the amount of current flowing through the charge controller. So there you go. You can adjust it. And so how do I actually adjust it? Well, over here at the positive terminal, remember, if you setting the voltage here ultimately sets the voltage here. So I have the, you know, my MCU, and I'm using, you know, PWM to set the voltage here. I have like an RC filter here so that you actually get like a stable voltage level rather than like the square wave. And then right here, I'm reading the voltage at the bottom of the charge controller, and that tells me, you know, the positive rail minus the voltage here tells me the voltage across the charge controller, and then that tells me how I need to set the current that's going, that's flowing through here. Okay, so that is the theory. So now what does this look like in terms of the circuit? Okay, so if you come over here, I have the circuit set up, and I feel like staring at the breadboard isn't terribly useful. Right, the connections are really hard to see, but you know, I have the MCU here, I have the op amp here, I have the MOSFET here with a big old heat sink connected to it, I have the, you know, the current shunt resistor right here, and I have a whole bunch of oscilloscope probes set up so I can actually show you things. And this is the power supply. It's at about 8 volts, and then over here is my DC load. So the DC load here, this is standing in for the charge controller, and why it's useful is that I can turn this knob and it adjusts the current draw. So this is like, you know, imagine this were this charge controller and it was drawing, you know, 0.4 amps, and it tells me the voltage that the charge controller would see at this level. And as you can see, you know, so at 0 amps being drawn, I'm at the open circuit voltage, it's like 7.5 volts for this simulated panel. And if I, you know, drive this up to like, you know, almost an amp, 0.8 amps, then, you know, that has no more voltage. That has no more voltage across my simulated, or sorry, across my charge controller here. Okay, so let's set that back down, and then now we can come over here to the scope and we can see what's what. So the top purple line is that pulse width modulated control signal, and as I change the current draw, you can see that the microcontroller is updating the duty cycle there on that. And then you know, so the blue line is the voltage drop across the resistor, the sense resistor, and the yellow line is the voltage at the bottom of the panel, and then the green line is the output of the op amp into the gate. Let's see, that is like the actual change in voltage on this is like very tiny. So let's see, can you see it there? There you go. Now you can actually see it moving around. But yeah, so that is the circuit. Now, one last thing I want to show you is that I can actually measure the IV curve of this simulated panel on my computer using the DC load. And when I do that, you'll see that it actually produces the right IV curve, you know, because you can't really tell from this oscilloscope if it's actually producing the right combination of voltages and currents. Okay, so here we are. We're going to measure the IV curve of our simulated solar panel. And so what I have here is, this is the serial output from the microcontroller. So I think, you know, this farthest column is the value being read from the ADC, so that's like the voltage. And then, I don't know, some other values that I forget what they are. What I have here is I have a script here. It's a Python script. It actually connects to my DC load, and it basically just you know, starts from 0 amps and goes up by, you know, 10 milliamps, and just walks up until it gets to 0 volts, and then it produces a nice IV curve for us. So I'm going to go ahead and run this, and we can see you know, what it looks like. So here you can see the output here. It's walking up, sweeping the input current 50 milliamps at a time, and you can see, you know, the wattage is climbing. We're getting closer to the maximum power point here, and then I think at around 700 milliamps it will collapse. Let's see, are we going down yet? Okay, no, we're still going up. 3 watts. Remember, it collapses pretty quickly, so it'll be pretty sudden. So I think around 700 milliamps is when it falls down. There we go. So it's starting to fall. There we go. Okay, so 831 milliamps is when we reach 0 volts, and now we can go ahead and moment of truth. Does it look like an IV curve? And yes, it does. It does indeed look like an IV curve. So the blue line is the IV curve, and then the blue line is the power curve, and you can see that our maximum power point is a little over 4 watts at I don't know 5.5 volts and about 800 milliamps. So there you go. This is very much like a prototype. I just kind of threw this together with parts I had laying around, components I had laying around. So I'm gonna spend some time probably trying to refine it a little bit, and but this is basically the basically how it's going to work, I think. So once I get all the little details worked out, I think it'll be a pretty nice piece of test equipment. The last thing I need to do is actually connect this up to a controller that uses MPPT, maximum power point tracking, to see if it can actually find the maximum power point of this simulated board, and there's not any weird like feedback loops between the controller and my simulated board. But I can't actually test that right now because basically all of the cheap chargers, even the ones that advertise maximum power point tracking, they don't actually really implement maximum power point tracking. They do something much simpler, which is something much simpler, like basically just like keep the input voltage some fixed percentage of the open circuit voltage. So I can't really test it with a real board right now. At least I don't think I can. Maybe I'll mess around with that. But anyway, yeah, thanks for watching, and until next time.